Hello and welcome. In this video, we are going to be talking about two new tests for convergence or divergence, the integral test and the P-series test. And then we're also going to be talking about a specific series called the Harmonic Series, which is a specially defined series that's going to help us in future videos and future lessons as well. So I look forward to working through this with you. Let's jump right in. So the integral test says if we have a function f of x that is positive, continuous, and decreasing as we get some x greater than or equal to some n value, which usually just comes from our sigma, and a sub n is basically we're defining the function as the rule of the series. Then either both the series and the integral converge, or both the series and the integral diverge, not necessarily to the same value. So let's talk about where this comes from and the idea behind it. The big idea behind it is the idea of using a Riemann sum to think about the relationship between a series and a function. So if we think back to what we talked about with improper integrals, if we have an integral, so based on this, the fact that it needs to be completely positive, it needs to be continuous, and the terms need to be decreasing or getting smaller. Here's a sample of what this function might look like. And we're defining f of x to basically be whatever this rule was. We're defining it as a function. If the area under the curve, thinking about it like a Riemann sum, if that converges, if we could find this area and this area was finite, then the integral would converge, and therefore the series, which is not continuous but just the sum of each of those terms, the series would also converge. If the area under the curve of the function diverges, therefore the series would also diverge. So we're saying a couple of things. We're comparing the area under the curve, again, only in the specific case where we have a function that is positive, continuous, and decreasing. We're saying if we take the improper integral of that, or we take the integral from some finite value up to infinity, we can conclude both convergence or divergence depending on the behavior of the function. So let's write out some of the things that we're saying here. So again, if the area under the curve is finite, if we can find that area, meaning we can evaluate the improper integral and get a value, then we could say that the area under the curve converges, which means that the series will also converge. Now, just because you can evaluate the integral and get a number doesn't mean that that is what the sum is converging to. So you can't say that, but you can say if I can take the improper integral and it converges, then so does this series. Similarly, if the area under the curve does not converge or it diverges, then so will the series. So the integral test comes into play, or the best time to use it is when you are looking at a series that you think, ooh, I could integrate that. It's usually one of the last tests that I try because having to evaluate an improper integral can be tedious and there's lots of room to make notational errors. But if you look at something and you think, ooh, I could integrate that function pretty easily, then this is a good choice. But remember, in order to use this test, the three conditions above must be met. So when you are using this test, you need to make sure you do the following things. The first thing you have to make sure that you do is define a function f of x, and that's coming from the a sub n term that is your general rule. So step one, define your f of x. The next thing you need to do is, in order to use this test, you have to state that these three conditions are met. You don't have to prove it. You should at least be mentally confirming, are all of the terms positive, continuous, and decreasing over some particular interval. So the second step is to state and confirm the conditions. So you have to state all three conditions. F of x is positive, decreasing, and continuous on some interval from n to infinity. And then what you're going to do is you're going to evaluate using limits the improper integral and show that it either converges, which would mean so does the series, or that it diverges, which means so does the series. So something that's great about this test is that you can conclude both convergence or divergence. Something that's not great about this test is there's 3 conditions that you have to confirm. You also have to define a function and evaluate an improper integral. So there's a lot of work that goes into using this integral test, but it can be a really helpful tool when you're finding convergence or divergence for that matter. All right, let's look at some examples. Okay, so first things first, we need to define our function. So I'm going to go ahead and say let f of x equal 1 over x squared plus 1. And I'm going to just say for x greater than or equal to 1, and I'm just saying that because that's what's here. And I'm going to say note that f is continuous, decreasing, and positive. All 3 things need to be true. You don't need to prove that they're true. If I look at this, if I plug in 1, if I plug in 2, the denominator is getting bigger. So it's definitely decreasing if we're only, actually regardless of the type of number we're plugging in, it's always going to be positive, and it is continuous everywhere. So those 3 things are true. So this is the very first thing you need to do. Define your function and state your conditions. Now we're going to consider the improper integral. So consider the integral from 1 to infinity of f of x dx, which will be equal to the limit as a approaches infinity of the integral from 1 to a of 1 over x squared plus 1 dx. And hopefully you can see right away that this is arctangent. So this is arctangent of x, and this is going to be evaluated from 1 to a. So this is the limit as a approaches infinity. The limit as a approaches infinity of arctangent, if I use direct substitution here, of a minus arctangent of 1. Now we should know that as arctangent goes to infinity, this is going to be pi over 2. As arctangent goes to 1, this is going to be pi over 4. So this limit is going to equal pi over 2 minus pi over 4. So we have shown that this integral converges. Therefore, since the integral from 1 to infinity of f of x dx converges, so does the series from n equals 1 to infinity of 1 over n squared plus 1 by the integral test. So we're defining our function and stating the conditions. We're considering the improper integral and evaluating it. If the integral converges, then the series converges by the integral test. Why don't you go ahead and pause the video and work through number 2 on your own. Then unpause the video and see how you did. So hopefully you've had a little time to work through this. So I've defined my function and stated my conditions. Now I'm going to consider the improper integral. Now, if you need to show work off to the side to actually evaluate this improper, or to evaluate the integral part of this, that's totally fine. You could just look at the unbounded integral of 1 over x natural log of x dx. And you could use u substitution. If you let u equal natural log of x, then du would be 1 over x dx. So this is going to become the integral of u to the negative first power du, which would end up giving you natural log of the absolute value of natural log of x plus c. So if you need to do scratch work off to the side, that's totally fine. If you don't think that a reader would need to see that scratch work, then cross it off afterwards so you don't have to worry about messing up the notation. You can use u substitution on this problem. You could also simply reverse the chain rule, although that one's a little more complicated to see. So this is going to be the limit as a approaches infinity of natural log of the natural log of the absolute value of the natural log of x. And we're evaluating this from 2 to a. So this is going to equal the limit as a approaches infinity of natural log of the absolute value of the natural log of a minus natural log of the absolute value of natural log of 2. As a goes to infinity, this is going to diverge. So what we can say is, since our integral is diverging, then the series is going to diverge. So since the integral from 2 to infinity of f of x dx diverges, so does the sum from 2 to infinity of 1 over n natural log of n by the integral test. Let's look at a couple more examples. All right, I encourage you, if you're feeling confident, to pause the video and work through 3 and 4 on your own. If you're not feeling so confident, then let's go ahead and work through number 3 together. So start out by defining your function and stating your conditions. So here we've done that. Now we're going to consider the improper integral. And if we find the antiderivative here, this is a pretty easy one to integrate. We would get negative e to the negative x, and we're evaluating that from 1 to a. So this is going to be the limit as a approaches infinity of negative e to the negative a minus negative e to the negative 1, which is going to give us, as a goes to infinity, this is really becoming 1 over e to the power of a, so 1 over e to the power of infinity. So that's going to 0, minus e to the negative first, so this is just going to equal 1 over e, which means that our integral converges, which means we can say, since the integral from 1 to infinity of f of x dx converges, so does the series from n equals 1 to infinity of 1 over e to the n by the integral test. Now I want you to look at this problem really quickly and see if there's a more efficient test to use that we have already used. And I'm hoping that maybe you're looking at this and saying, isn't this geometric? We could rewrite this as 1 over e to the power of n. So we could actually use the geometric series test. 1 over e is less than 1. Therefore, this series converges by the geometric series test. So don't forget all the tests that we've learned up to this point. The integral test is not the most efficient. There's a lot of tedious work that goes into it. So it's great for us to practice using it. But make sure anytime you're looking at a series problem that you're really thinking through what we've learned and using the most logical test for each problem. All right, I'm going to encourage you to do number 4 on your own and then unpause the video and see how you did. So step 1, define your function, state the conditions. Step 2, evaluate the improper integral. To evaluate this integral, you're either going to need to use substitution or reverse the chain rule. If I have a 3 here, then I have the derivative of this inside function, and I can do that as long as I have a 1/3 here, and then I'm going to go ahead and find that antiderivative. So one of these 1/3 comes from having to put it in front of the integral, and the negative 1/3 comes from dividing by the new exponent. So let's clean this up a little bit. So here is that cleaned up a little bit and using direct substitution. This term is going to go to 0. So I'm going to be left with negative 1/9 times 1 over 3 cubed, which we can leave just like this, times negative that. So this is going to end up being, if I wanted to simplify it, positive 1 over 9 times 27. That's really as simplified as I want to get here. What that means is that this interval converges, which is all we really care about. We don't care about that value, because now we can conclude that since the integral converges, so does the series. And there you have it. So remember, the one last thing I want to say about the integral test is that it doesn't always work. It doesn't work for every type of functions. What we're going to do next is we're going to look at a couple of problems that you can't use the integral test on, and I want you to be able to identify why you can't use the integral test in those cases. So here we go. Go ahead and look at these two functions and figure out why we can't, look at these two series and figure out why we can't use the integral test on these two series. Then unpause the video and see how you did. So the first series here actually doesn't meet any of the requirements. It's not continuous. It's not continuous when n equals 2, or it's discontinuous. Some of the terms are negative. The first term would be negative 1, and it's not always decreasing. If you look at the second one, the very first thing that I notice is that this is an increasing, so we can't use it. It is continuous, and it does look like all the terms are going to be positive since we start at 3, but since it's increasing, we would not be able to use the integral test. So Make sure you define your function, you confirm that the three conditions are met, and then you can evaluate the improper integral and come to a conclusion based on the integral's convergence or divergence. So let's take what we've just learned and apply it to one of the most well-known series that there are, the harmonic series. So this series here, the series as n goes from 1 to infinity of 1 over n, is known as the harmonic series. And if you think about this series, and even if I was just to write out a few terms, this would be 1 plus 1/2 plus 1/3 plus 1/4 plus ... I want you to make a decision based on whether you think this series is going to converge or diverge just based on the way that it's behaving and what you're seeing right now. So go ahead and make a hypothesis. Now this series, if we look at these terms, all of these terms are positive, they are decreasing, and they are continuous. So this is a great candidate to use the integral test on. And if we think back to the other tests that we've learned so far, the limit as n approaches infinity of 1 over n would be 0, so we can't use the nth term test. This is not a geometric series. So really at this moment, the only test that we have is the integral test that could apply. So go ahead and perform the integral test here and determine if the series converges or diverges, and then unpause the video and see how you did. So here I've defined my function. Now I'm going to consider the improper integral from 1 to infinity. And then to evaluate that improper integral, I need to take the limit as a goes to infinity of the integral from 1 to a of 1 over x dx, and then go ahead and evaluate that. So finding the antiderivative using direct substitution, natural log of 1 is 0. Natural log of the absolute value of a, so natural log grows forever, even though it grows really slowly. So this piece right here diverges, which means that the integral is going to diverge. And what the integral test tells us is that if the integral diverges, so does the series from n equals 1 to infinity of 1 over n is going to diverge by the integral test. Now, that may have been exactly what you thought was going to happen, but when I first looked at this series, my gut was that this series is going to converge. 1 over n, I have numbers that are getting smaller and smaller and smaller, and each time I cut them into smaller pieces, it seems like this is converging towards 0. Each term is converging towards 0, but the sum, which we'll actually look at another really interesting proof of this, the sum is not actually converging to 0. It's not converging at all. It's getting bigger and bigger and bigger, even though our terms are getting smaller. And we just verified that using the integral test. We will show this using the comparison test a little bit later on once we learn some more tests. But this is a great application of using the integral test on the harmonic series. Something I want you to know is now that we have proven this, you can use the fact that the harmonic series diverges. So you can use the fact that the harmonic series diverges. You do not have to prove it again, although what we just showed is that you could pretty easily prove it using the integral test. So now the next thing you might be wondering is, okay, if I have a series of this form, but maybe there was a different exponent here, what would happen if p was 2 or 1/2 or 1/4? At what point is it going to converge or diverge? And if that is where your mind went, this kind of series has a special name. This type of series is called a p-series, and there's a specific test for series that are of that form, and that's what we're going to look into next. But the harmonic series, when that p-value in this case would be 1, the harmonic series is going to diverge. But let's look at what happens in other cases where p is not equal to 1. So the p-series says, in any series of this form, so that's the key thing here. If we're talking about a p-series, it has to be of the form, our rule has to be of the form 1 over n to the p. Not 1 over n to the p minus 5, not something totally different. It has to be of this exact form, which makes this test very specific, but it's also a really wonderful test that works efficiently when we have a series of this form. Any series where p is a positive constant and has this structure converges if p is greater than 1 and diverges if p is between 0 and 1. So something to notice, we're not talking about p being a negative number, because if p was a negative number, then we would have 1 over n to the negative p, which would be the same thing as n to the positive p. That's no longer of the form of a p series, and in all likelihood, this is going to be a series that you could use the nth term test on to prove that it diverges. So we are looking at what happens when p is greater than 1 or when p is between 0 and 1. So when p is a non-negative number. So let's go ahead and prove this, and we're not going to prove the case specifically for p equals 1. I'm just going to say, note, if p equals 1, this is the harmonic series, which we just proved diverges. So now we're going to use the same test that we just used on the harmonic series to look at this series, this p series. So let f of x be 1 over x to the power of p, where p is a positive constant, there we go, and x is greater than or equal to 1, f is continuous, decreasing, and positive. So we can consider the integral from 1 to infinity of f of x dx, and we can look at that using limits from 1 to infinity of 1 over x to the p dx. Now remember, this p is a constant, so we can integrate with respect to p, we can integrate with respect to x. This is going to be, I'm going to rewrite this as x to the negative p. So if I was integrating that, I would add 1 to the exponent, and I would divide by that new exponent, right? Negative p plus 1. And this needs to be evaluated from 1 to a. So this would be the limit as a approaches infinity of, now I'm substituting a in for x. So a to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Now this part of the integral is going to converge regardless. Since p is a constant, I have 1's and p's over there, that's a constant. What I want to think about is when is this going to converge? Well, this is going to converge as long as negative p plus 1 is less than 0, right? As long as this exponent is still negative, this will go into the denominator of the fraction. And as a goes to infinity, we'll have 1 over infinity, which is going to be 0. So as long as negative p plus 1 is less than 0, this integral will converge. So if I solve for p here, if I subtract 1, negative p is less than negative 1. So p must be greater than 1 in order for this to converge. Which means, therefore, since we said it has to be positive, it will diverge if p is between 0 and 1, including 1. So a couple of things to note about this test, and I'm going to try and add a little box in here. You have to identify when you're using this test that p equals some number, and then you need to talk about how it relates to the number 1. So p is 5. 5 is greater than 1. Then you can say, therefore, by the p series test, and you can draw conclusions about both convergence or divergence using this test. So really great test, incredibly quick and efficient to use, but it has to be a series that is of the form 1 over n to the power of p. So let's work through some examples, and then we'll go ahead and wrap up this video. All right, I want to work through 7 and 8 with you so that you can get an idea of how this works, and then I want you to try 9, 10, and 11 on your own. So this is a p series. This is a p series, and p is equal to 1/2. Since this could be rewritten as 1 over n to the power of 1/2. 1/2 is less than 1. Therefore, the series from n equals 1 to infinity of 1 over the square root of n diverges by the p series test. So you need to identify that it's a p-series, what p is, and how that relates to 1, and then you can simply jump to the conclusion that p is either going to converge or diverge. So here on number 8, this is a p-series with p equal to 2, which is greater than 1. Therefore, the sum from 1 to infinity of 1 over n squared will converge by the p-series test. So again, really straightforward. Point out that it's a p-series, identify what your p-value is, compare it to 1, and then draw your conclusion. Go ahead and work through 9, 10, and 11 on your own, and then unpause the video and see how you did. So here on number 9, it might be helpful to rewrite this in sigma notation so that you can identify that it's a p-series. You don't have to explicitly write it in sigma notation since it wasn't given to you in that way, but then you can identify that this is the series 1 over n to the power of 3 over 2, and that's a p-series where 3 over 2 is greater than 1, therefore it converges by the p-series test. Similarly, on number 10, this is a p-series where p is 5 over 4, which is greater than 1. Therefore, that one converges by the p-series test as well. On number 11, the first thing that you need to use are rules of exponents in order to rewrite this as a p-series, because in its current state, it is not. So in this case, p is going to be 1 over 15, which means this series is going to diverge by the p-series test. So key concepts in this section. We talked about the integral test and how that relates to Riemann sums, how when you're using the integral test, you need to define your function f of x. You need to state the conditions that it's positive, decreasing, and continuous. And then you need to actually evaluate the improper integral using appropriate notation. We used that to prove both the harmonic series diverges and to prove the p-series test. To use the p-series test, you just need to make sure that you have a series that is of that form, identify the p-value and how that relates to 1, and then you can conclude either convergence or divergence. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.